Okay, I think it's working. So, hello everyone, and welcome to our meeting. I'm gonna start presenting a paper, and next is gonna be Jose Roberto. Okay, so can you all see my screen? Please confirm. Can you all see my screen? Okay. So the paper I choose to could you close the door, please? The paper I choose to present today is this, explaining the gamma gamma plus X excesses at 151 GeV via Drell-Yan production of a Higgs triplet. So the idea is to explain anomalies that comes from multi-lepton searches and narrow resonance that indicates the existence of a new particle, a scalar, in the 151 GeV or in between 140. Let me see. This is somewhere down there, but I don't remember. Is in the range of mass that is this range implies a 151 GeV new scalar. So to explain this excess, the paper uses an extended model extended, which is the delta SM model, which includes a new scalar, a triplet scalar, and as we will see, this scalar needs to have a neutral component. That this neutral component could explain this anomaly. Okay, so one of the implications of this anomaly specifically is that this new scalar should couple to the W boson, but not doesn't have a couple to the Z boson. So it has a sizable branching fraction of this new scalar into WW, but the branching fraction into ZZ was not observed. So this means that this scalar must have a zero charge, and it must have a zero hypercharge. So the triplet that they choose is a triplet coming from the SU2 left symmetry, and it's a triplet with zero hypercharge. Okay, this triplet has three components, of course. They have a positively charged component, a negatively charged component, and a neutral component. And this neutral component would be this new particle that interacts with the W and not the Z, and could explain this anomaly. Okay, so to produce this boson, they use the Drell-Yan process, PP going to W and generating this delta zero and delta plus or minus. Okay, and they use the Atlas analysis to search for this signal, and in the standard model Higgs in the diphoton channel. So they generate diphoton plus, as the name says, diphoton plus X. This X I'm gonna explain later what it is, and they use this analysis to interpret this result using this new model. Okay, when you include this scalar, it will gonna influentiate the W mass. So the W mass we're gonna have a slightly shift to the positive shift, and this positive shift is related to the custodial symmetry that I'm gonna talk later. They use the 22 signal category used by Atlas, but they only choose 10 of them. I'm gonna show you later what they use, and to constrain this model. Okay, so I'm gonna jump into the signal. This is the signal that they search. It's not the only way to generate those scalars, but it is the most prominent way. So you have a PP generating a W, which is a virtual particle. Here we have this cross, which is virtual. The decay into a neutral scalar, a charge scalar. This neutral scalar decay into diphotons, and this X and Y are W and Z, T and B, C and S, or tau and the respective neutrinos. Okay? So, one important thing to mention is that after the electroweak symmetry breaking, this new scalar gets a VAV, and this VAV influentiates the mass of the W boson. How is that? So I'm gonna show in the board. Sorry for the ones that are in the meeting. In this model, the mass of the Z is equal to G squared over 4 cosine of 1. Can you please divide one? The mass of the Z is the same in the standard model, G over 4 cosine squared VAV. This is the standard model VAV. And the mass of the W is going to be G squared over 4, the VAV of the standard model, plus 4 times the VAV of this new scalar. So the mass of the Z maintains as the standard model, and the mass of the W increases by this factor. Okay, but the mass of the W is measured. It's a fixed number with a error bar, but this error bar permits the increase of about 40 MeV in the W mass, and they use this increase to say, okay, we could have this new VAV in this new formula for the W mass involving this new scale. Okay, so we use this fact to explain why this mass could increase. So again, if you use this model, the W mass would increase, and this increase is also responsible for the custodial symmetry breaking. The custodial symmetry, the important part of the custodial symmetry is that it protects the relationship between the mass of the W and the mass of the Z. So you have this parameter here, which is the rho parameter, which is equal to the mass of the W squared over the mass of the Z squared cosine theta W, and this is approximately equal to 1. Okay, but if you change the mass of the W and don't change the mass of the Z, you're gonna have a different rho parameter. It will not be equal to 1. So it will break the custodial symmetry in a way that it changes the W mass but doesn't change the Z mass. If the changes were equal, it could cancel and it would still be 1. Okay? So this is a nice aspect that they comment in the paper. And using this analysis, you can say that the new VAV for the scalar is in the order of GeV, as they say here. Is in the order of the GeV. Okay? So, as I said before, the model they include a SU2 left triplet scalar with hypercharge equal to 0. This triplet in the scalar sector of this model includes the Higgs, the charge scalars, the neutron one, only those fields. The neutron gets this VAV, as I said before, and they analyze these processes that generate those scalars. You have two processes here, PP going to delta 0 and delta charged, and PP going to delta charged. But as you can see, the cross-section is greater for the process above, so it's the leading process in this scenario. And as you can see, the branching ratio between of the charge scalars going to X and Y remembering X and Y are W, Z, T and B, CNS, tau, and neutrino. They change according to the mass. They consider the mass, because of the VEV, they consider the mass of the neutral scalar equal to the mass of the, approximately equal to the mass of the charge scalar. And when we increase the mass, the production of W and Z becomes larger than the production of the other channels. So if you want to explain the anomaly in the 151 GeV, the more prominent signal that you're going to have is the signal involving PP going to delta 0, delta plus and minus, and decaying to W and Z bosons. Okay? One important aspect of this is that the W and the Z, they generate leptons, they generate quarks, they generate, so leptons including neutrinos. So they are gonna, in the collider, the signature would be leptons generating the final state, missing energy because of the neutrinos, and jets because of the quarks being generated by the Z, by the W. Okay, so they're not standard model neutrinos. They don't include new types of neutrinos. They only include scalars in this case. So they use these signal regions here. So they use high jet activities, top, leptons, missing energy, as I said, they use those analyses of Atlas to generate explicitly this plot here, okay, which is the 95 confidence level upper limit on the branching ratio of the neutral scalar going to gamma gamma. Okay, so they have here the 10 signal regions that they observed that were more relevant for this approach. And I don't know if you can see, but there are two regions here in this graph that the limits get weakened. So this limit implies that all that is above those lines are excluded because it's an upper limit on the branch ratio. So when the limit goes up, when the graph goes up, the limit weakness, because you have a smaller region of the parameter space which is excluded. Okay, so the limit get weakened in 151 GeV, and they get weak in this region here. Okay, that we are going to see in the next graph. So they use a likelihood approach to generate those graphs, and multiplying those likelihoods of those graphs, they found this other graph here, which is, as I said, is the same thing. They have peaks in these regions. This peak, they represent the 151 GeV particle, and this peak, they say that this is a combination of the Higgs and this new scalar that generate this new peak. This first one has 3 sigma of significance, and this one have I think 2 sigma of significance. So they say that the standard model could be extended using scalars, of course. They say that this could be an explanation for this signal, but they say that the other scalars could be added, other analysis could be made to explain these signals and other signals. It is not a complete it's not a complete way to describe this. You can make this in a lot of ways. This is just one of them. Okay, so they say that those analyses could be improved in the run tree of LHC, of course, in the FCCH8 in high luminosity, and that's basically it in the article. So, anyone have questions? I looked for other articles made by those researchers, and they work on these types of model and this anomaly a lot. So this is one of the main topics of those papers of those guys. So it's basically this. Okay.
What are the prospects about these papers? What they are planning to do after this the new collider, new experiments? They are planning to study more about this type of signals.
Yes, because the FCC-EE will work on the energy of the Z, right? So the only difference, in principle, the only difference is the luminosity. So if you have more luminosity, you have more data. If you have more data, the significance of your signals could be being greater. So
Yeah.
if this process occur, you're gonna see it occurring. You're gonna see this bump. But if it doesn't occur, the bump is gonna disappear in the signal. So more. So
have a lot of models that have scalars like this, so you can throw
Or other type of model.
other kind of models.
yeah, basically this. Okay.
So thank you. Thank the speaker.
I'm gonna close here and end the stream. Okay,
Yeah.
thank you guys. We're gonna start a new stream afterwards. So end the stream.
Yeah.